Hi everyone, welcome back to this seminar. Today we have the Lamplighter from Paris. Well, the picture is Lamplighter from Paris. It's Florent Baudier from Texas A&M, and he's speaking on L1 embeddability of Lamplighter metrics. Florent, you can come in the picture now.
All right, thank you, Benjamin, for the introduction. Well, everybody has mentioned this already, that it was a great idea to have these webinars, and I definitely second that. Anything that can bring the Banach space community at large together, it's an excellent idea. So thank you, Benjamin, for that. So I'll share my screen. So what I want to talk about today is motivated by a construction in group theory, which is the Lamplighter construction, and I will talk about joint work with Pavlos Motakis, Thomas Schlumpfrecht, and Andras Jacques, and so we have two papers on this topic, so I'll talk mostly about the second paper, but we need a result from the first paper as well. So the motivation is comes from geometry group theory. So let me make a very brief excursion in group theory and define what is this Lamplighter construction. So if you have a group gamma, okay, and so gamma is a group, and if I denote by Z2 the group with two elements, so with the addition, so what I can define is the Lamplighter group over gamma, which is Z2 with gamma, so it's a Ries product. And so what is this group? So this group, so you look at the functions from gamma into Z2, and you take the cross product with gamma. So this is just the set of functions from gamma into Z2 that have finite support. So by finite support, I mean that the function takes the value 1 only finitely many times. Okay, it's not the identity for only finitely many elements. And so you can equate this product with the following operation. So if you look at two elements fx and gy, so the group product is the following. So for the second coordinate, you just take the product in the group gamma, and for the first coordinate, so here you're dealing with functions, so you can define the following function. So you're going to look at f of z plus, so if you just add g of z, you just take the cross product. So here you look at g applied to the element x inverse times z. Okay. So this is just this is a little twist compared to the group, to the classical operation on the group, but this has a strong influence on the geometry and the algebraic properties of the group. Okay, so Lamplighter groups. So these are particular example of semi-direct products. Okay, so here the action is the action of gamma on the functions on gamma taking value into Z2, where the action is just by left translation. Okay, so this is one example of a semi-direct product, and it's very well. There is a lot of study going on about understanding how general Ries products of group can be embedded into Banach spaces and understand the quality of the embeddings and the influence on the parts of the groups. So this is the definition. And so what is important for us is that so if gamma is finitely generated, then the Rives product is also finitely generated. Okay. So and this is because of the way the first coordinate is defined. Okay. So which means that we're dealing with finitely generated groups, and so this is well known that every finitely generated group, you can look at it from a metric perspective, because you can look at a Cayley graph of this group, and you can equip the Cayley graph with the graph metric. So this turns your group into a geometric object. Okay, so I'll be interested in embedding these groups viewed as metric spaces into some Banach spaces. Okay. So then you need to understand the word metric on this group, and from the definition I gave, it might not be completely obvious what is this metric. So I will switch now to the graph setting. So, and I will define Lamplighter graphs. So this is an extension of the Lamplighter construction. Okay, and so how do we define the Lamplighter construction for a graph? So assume that you have a graph VE. So this is a graph, and what I want to define is a new graph that I would call Lamplighter over G with the following operation. So the vertices are so the set V times, so if V is finite, it's just going to be the power set of V. So I'm mostly going to talk about finite graphs, but otherwise you just take the finite subsets of V. So this is the set of vertices, and the adjacency relation is defined as follow. So this is a generic point in your graph. So you have a point and you have a subset, and we will say that XA is adjacent to YB if and only if. So there are two options. So either A equals B and X is adjacent to Y. So this is adjacency in the graph G, or so X equals Y and the symmetric difference between A and B is X. Okay, so I will refer to this to the first edge as a move edge, and for the second edge as a switch edge. So this is one way to model a Lamplighter construction. So this is the move or switch model, and so this extends the Lamplighter construction for groups for the canonical set of generators for your Lamplighter group. And because there is a natural identification between functions from gamma into Z2 with subsets. Okay. So now what is the graph metric here? So well, you just take the length of the shortest path on this new graph, but it has an exact formula. So let me try to explain this using a picture. Okay, so here we have something that depicts so the ground graph G. Okay, so let's say this is the graph G, and think of this as a street map. Okay, where at each intersection of streets you have a lamp. Okay, which can be turned on or off. And now assume that you start here and you want to go there, and you have to switch this line that is on and you want to switch it off, and this light that is off, you want to switch it on. So how would you do? So you would walk on your space here, and you would go to this lamp here, and then you would switch this light from on to off. Then you would walk here, and then you would switch this light from off to on, and then you will continue to your destination. Okay, so you should think of this as horizontal moves on the graph, and then vertical moves when you have to switch the lights on and off. So once you have this picture in mind, so the lamplighter distance between XA and YB, so this is, there is a traveling salesman problem involved. Okay, so I will explain in a second. Okay, and then you have, you need to account for the cost of switching the lights on and off. So this part here, this is a traveling salesman problem, which starts at X, which starts at X, visit all the points in the symmetric difference, and then finishes at Y. Okay, so the points in the symmetric difference is the points that have to be switched on or switched off. Okay, so so when you have a generic point here, so X is the position of the lamplighter, and A should be thought of as the configuration of lamps that are on. All right, so you want to go from one location to another location and go from one configuration to another configuration. Okay, so there is this natural traveling salesman problem that pops in here, and this actually makes the problem difficult because it's notorious that traveling salesman problems are NP hard, so you cannot expect to have an exact to find an exact solution easily. And but this makes also the problem of studying these lamplighter groups or graph interesting. So so I am interested in embedding these spaces into an L1 space. Okay, so let me review briefly some notions from metric geometry. So what I define as C1 of X, so this is going to be the L1 distortion of a metric space. So here X dx is a metric space. Okay, so this is the smallest d greater than 1, such that so there exists a map from X into an L1 space. Okay, so if your space is finite, you can always take some finite dimensional L1, such that, so for every pair of points in X, we have the following inequality. So the map is going to be D-Lipschitz and non-contracting. So here my target space is a Banach space, so I can always assume that I can rescale so that the map here is non-contracting. Okay. So the distortion is really witnessed by this constant d. So there is the bi-Lipschitz embedding, and the distortion of this embedding is at most d, and you look at the smallest d such that this is possible. Okay. So what do we know about bi-Lipschitz embedding of lamplighter groups into L1? Well, we don't know that much. So there are results of Naur and Perez saying the following thing. So if you look at the L1 distortion of Z2 with Z, well, this is finite. So this just means that there is a bi-Lipschitz embedding of Z2 with Z into L1. And they also showed that if you look at the L1 distortion of Z2 with Zn, so this is a cycle. Zn is the graph of Zn is a cycle. So this is a finite metric space now. So, but it has bounded distortion uniformly in N. So that's what I will denote by big O of 1. So there is some universal constant that does not depend on N, such that there is an embedding with this distortion. So this embedding here into L1 was extended to by Lipschitz embedding into every non-supereffective Banach spaces by Beata, Ranjay-Antoine, and Mikhail Ostrovsky. And so there is another result of the Cornulier, Stalder, and Valette, which says that if you look at the L1 distortion of the Lamplighter group over a free group, so this is the free group with K generators. So K is fixed, okay. So, well, you can embed by Lipschitz this Lamplighter group into L1. So this is this result is a byproduct of a study of proper isometric actions of groups into Banach spaces, but you can get this from their work. Okay. So what do these groups have in common? Well, they have in common that if you look at the traveling salesman problem on these groups, so on Z, on Zn, which is a cycle, on the free group, which is a tree, well, the traveling salesman problem is tractable. I mean, you can definitely come up with exact formulas for this because the combinatorial structure, the topological structure of this graph is actually very simple. Okay, and so, and that's what we know. So these results were proved like 10 years ago, something. So now I want to talk about the planar Lamplighter problem. Okay. So this comes out of a work of Naur and Perez. So they showed the following result. So this also was proved about 10 years ago. So they showed the following result. So for every epsilon positive, there exists some constant that depends on epsilon. And there exists a map from Z2 with gamma into L1. So what is gamma? I forgot to mention this. So gamma here is a group of polynomial growth. Okay, so gamma, it's a finitely generated group with polynomial growth. So what is the growth of a group? So these are finitely generated groups. So the balls, they have finitely many elements. And actually the number of elements does not depend on the center of the ball. And polynomial growth just means that the number of elements in a ball of radius R is polynomial in R. Okay, so R squared or to some power. Okay. So so these are well-studied groups. So what they showed is that there exists a map from any Lamplighter group over a polynomial growth group into L1 such that what? So for every xi in the group, we have the following. So the N1 norm is less than this constant k times the distance between x and y, and at least distance between x and y to the power 1 minus epsilon. Okay. So this is not a by Lipschitz embedding because of this power here. So this is a weaker notion of embedding. So geometric group theory, this is so an embedding with a compression exponent. And this says that you can choose epsilon as small as you want. So it falls by a small margin to be a by Lipschitz embedding. Okay. So this means that the compression to embed this group here into L1 is 1, okay? But 1 is not necessarily attained. So they proved the following result. And so there is the following problem. So this was stated in Naur and Perez. So is the L1 distortion of Z2 with Z square finite? Okay. So we don't even know for the planar Lamplighter group if this group can be by Lipschitz embeddable into L1. Okay. So this, I mean, shows how much remains to be understood about Lamplighter groups, and maybe how difficult it is to come up with embeddings into Banach spaces. Okay. So so Z square is just, I mean, the Cayley graph of this square is just a two-dimensional grid, integer grid. Okay. So there is an important remark here, which is the role of this constant here, K epsilon. So it turns out that if you look at the proof, and if you track down the dependence on epsilon, so you can easily see that the dependence on epsilon is polynomial, okay, for some constant C, so which in general can be taken less than 3, and C is less than 2 if gamma embeds into, let's say, a Hilbert space by Lipschitz. Okay. So this is what you can get from the proof. Now it's definitely possible, it might be true, that you can decrease this exponent by 1 by really looking at deeper at the proof and try to fine-tune the argument and optimize some parameters. So you can probably get C equals 1 or 2 in the general case, okay? But this is, you have to somehow rework the proof a little bit to do that. But this is definitely something that is possible, okay? So why is this important? So this is important because if you take epsilon to be 1 over log of n, okay? So, so then what you have, if you have a map from Z2 with gamma into L1 that satisfies the following inequalities. So here you have the constant of epsilon. So if epsilon is 1 over epsilon to the C, if you take epsilon equals log of n, you would get some constant times log of n to this power C, whatever is the power, times the distance between x and y. And then you would have a lower bound. So the lower bound, you have the distance between x and y over the distance between x and y to the power epsilon. But epsilon is 1 over log n. So if you take points that are at distance at most some factor times n to some power, so polynomial in n. So this quantity here becomes a constant because n to 1 over log n is just a constant, okay? So what you get is a lower bound like this, eventually with some constant. So this says that if you restrict your map to sets of diameter polynomial in n, well, then you get a by Lipschitz embedding with this distortion here, okay, of log n, logarithmic in n. And from this, you can deduce that the L1 distortion of the toric Lamplighter groups, so fix some k, okay, k is fixed, it's the k-dimensional discrete torus. So you get an upper bound for this, which is Vigo of log of n, okay? Now, how many points do you have in your Lamplighter groups? well, you have the number of points in your graph, but you have also the number of subsets, right? So this is exponential in NK here. So for this, you can easily see that you get a log of the number of points in the group. Okay. And so if you know Bourgain's result, so Bourgain's famous embedding theorem says the following. So for every metric space X, the L1 distortion of X is at most a constant times log of the number of points. Okay. So this is a bound that you get for every metric space. And the bound here is actually an exponential improvement over Bourgain's general bound. So you have a doubly logarithmic bound on the number of points. Okay. So for the toric Lamplighter groups, you have this improvement over Bourgain's general bound. And the main result that I want to describe in this talk is the following result that we obtained with Pavlos, Thomas, and Andras. So if you take X to be any Lamplighter group, or any Lamplighter graph, and actually, for that matter, any Lamplighter metric space, which I will define in a second. So Y will be a metric space here. You can define what is the Lamplighter metric over this space. So this gives you a new metric space. So then the L1 distortion of X is actually a big O of log of the cardinality of X. Okay. So I think this is quite remarkable that if you look at Lamplighter metrics, so the general bound that you can get is doubly logarithmic in the number of points. Okay, so it's not just true for these toric Lamplighter groups, but it's actually true for any finite group. Okay, any finite Lamplighter group. So so now in the remaining time, I will explain the proof, and I will give you some intuition for the techniques that are employed to prove this. So as I said, here we're gonna put ourselves now in a context that is maybe the most general context you can think of, which is the context of metric spaces. So I started with group, then I talked about the construction about graphs, but you can actually extend this also easily to any metric space. So Lamplighter metrics. So you just define this in the most natural way. So now you have the metric space X. Okay, and what I want to define is the Lamplighter metric associated to X. So this is going to be a metric on the set X cross 2 to the X, and you're going to equip this with a metric. So the metric is just essentially going to copy and paste the formula that I wrote before. So you need to solve the traveling salesman problem, and to account for changing the lights. Okay. So this is you can recognize this as the symmetric difference between subsets. So this is a well-known metric, and this part here that I will denote by tau of XA YB. So this is what we'll call the traveling salesman semi-metric. It's actually not a metric because you can have points that are distinct but such that this quantity is 0. But this is really a minor detail. When you add the symmetric difference metric, then you recover a genuine metric. So here maybe what do I mean by a traveling salesman problem here in this metric space? So it's very natural. You just look at the complete graph. So you can always realize a metric space as a weighted graph, right? So look at the complete graph on X. So you have an edge between every pair of points, and you put a weight on this edge, which is the distance between these 2 points. So this is a weighted graph. So it's the complete weighted graph, and the shortest path distance is just the distance between the points, okay? So that's what I mean here by the traveling salesman problem here. And so I will look at the traveling salesman space over X, which is just X cross 2 to the X, equipped with this semi-metric, okay? Because we're trying to embed into L1. But this, the symmetric difference metric, it's well known that it embeds into L1. And so we can just focus on this semi-metric here and try to embed this space into L1. So we will do so from now on. And we will forget about this part here because this naturally embeds into L1. Okay. So, in our first paper, we proved an extension of the Cornulier-Stadler-Vallet result about the free group. So the free group, it's a tree, right? But it's a very regular tree. It's an infinite tree. So what we proved is that if you take the Lamplighter graph over any tree, so finite, infinite, not even countable, doesn't matter, then you can embed this into L1 with some bounded distortion. And actually, with our proof, it's easy to track down the bound with distortion at most 6. Okay, but we were only interested in unweighted graphs. But it turns out that essentially the same proof works for a weighted graphs or weighted trees. So if you look at the traveling salesman space over, so this is a tree, so this is a combinatorial tree, and you equip this tree with a weighted distance. So you put weights on the edges and you look at the shortest path distance. So you can embed this space into L1 with distortion at most 6. It's not really important what is the constant, but since we have access to it easily, I want to mention it. Okay, so so why is this true? So let me just give the very brief idea of why this is true. So that's not okay. Okay, so so I forgot to erase the design. So that's okay. So here, so this is the graph of a tree. Okay, and assume that we want to start at X and go to Y and visit all these orange vertices. So the orange vertices, they represent the symmetric difference between A and B. Okay, so you want to visit all these points. So how would you do this on a tree? Well, you don't have many options, right? So what you do, you start from X, and then you go visit these points, you backtrack, you go visit these 2 points, you backtrack, and you keep doing this, right? So this is pretty straightforward how you do this, and then you finish there. So now when you try to estimate this, this distance, well, this path here, which is kind of the main path between X and Y, so there is just one geodesic. So you walk on this path only once, okay? So for all the other edges, you walk on them twice because you have to backtrack. So you can easily come up with a closed formula that gives you the solution of the traveling salesman problem on a tree, okay? And once you have this formula, well, you need to, then it's a matter of counting. And when you embed into L1, then this is something that can be done fairly well. So that's why you can really handle the traveling salesman problem on a tree. So and you can do this if you have weights. So this is still very far from the general result that I announced earlier. So you want maybe to try to see if you can reduce your general problem to a problem to the problem on the tree, right? And so this is what I will discuss now. So can we reduce the problem to the case where we have the construction on the tree? Okay. So the most naive thing to try is to say, well, let's try to embed. So this is a bi-Lipschitz problem. Let's try to embed a metric space into a tree and see if we can use this information. So of course, this is too naive, and it breaks down actually at the fairly early stage, because if you want to embed Cn, so Cn is the n cycle by Lipschitz into a tree. So take any tree T. So any embedding of the nth cycle into any tree will incur some distortion that is at least, so big omega of n, at least a constant fraction of n. So this is definitely not difficult to see, and intuitively it's clear. You're trying to embed a cycle into a graph that is acyclic, right? So there has to be some distortion, okay? So, and this is pretty bad. It's proportional to n, okay? So there's no way that this naive idea can work, okay? But you can get around this. So what I will discuss now is actually a beautiful idea that has been around in computer science for probably 25 years, I guess. So this is a very standard technique in theoretical computer science, because when you want to design an algorithm, usually if your graph is a tree, you can do this fairly easily. And then you want to reduce your problem to trees, okay? And try to leverage the algorithm that you came up for a tree to a general graph. So this idea is usually attributed to Karp, so the famous computer scientist, famous for his work on NP hardness, NP completeness, and many other things. But I think it was never published, but then he appeared in a paper with Nogalen, so Karp, Peleg, and West. So this goes back to the late 80s, beginning of the 90s. Well, so the idea is very simple. So let's go back to this cycle example. So let's say that you have a cycle, okay? And so you have your cycle like this, okay? So you have your vertices. And so what you want to do is to look at the map that embeds the cycle into itself, but you will delete an edge, okay? So let's delete this edge, for instance, right? So when you delete an edge of a cycle, obviously you obtain a tree. I mean, it's a very simple tree. It's just a path, and then you just send the points to themselves. Okay, so you will send this one to that one, this one to that one, and so on. Okay, so it's just the identity map. And so what does this map do? So you have a map from Cn into a tree, actually. So it's actually a path. And so let's try to understand the distortion incurred by this map. So if you look at the distance in the tree between the images of 2 points, well, this does not contract the distances. So this is pretty clear, because you're deleting an edge. So you can only increase the distances, okay? And what about the expansion? So the expansion, well, if you look at these 2 points here, these two vertices here, definitely there is some expansion, because if the distance was 1 here, now you cannot connect these two guys, so you have to walk all around the cycle here to be able to get to the other side. So this guy gets a distortion of n-1. Okay. And for the other, and that's the edge that is stretched the most. Okay. So you get this actually for every xy in the cycle. Now this is really a very simple but very powerful and beautiful idea is you can just randomly delete an edge in the cycle, okay, and try to understand on average what would be the distortion, okay. So here I deleted 1 edge, but actually I can delete n edges. So what I get is I get n maps from a cycle to a tree, okay. And so when you look at the distance between x and y, so this is obviously non-contracting, but then when you look on average, what is the distance? Okay, so look on average, what is the distance? So if I go back to my picture here, these two guys here, there is only 1 edge deletion that will disrupt their original distance. Okay, for all the others, you will have actually the same distance. So if you do a little bit of simple computations, you have n-1 distortion for when you delete the edge between these two vertices. And then for all the others, you don't change anything, but then you have n-1 other trees. So you have 2 n-1, and then you take the average. And this is actually less than 2. So very simple idea. So you can probabilistically embed your cycle into trees with bounded average distortion. Okay, and all your maps are non-contracting. All right. So and actually, it turns out that for them it was enough to be able to leverage this algorithm for trees to algorithm for general graphs for some important theoretical computer science algorithmic problems. So Bartal came up with the following definition and proved some very interesting results. So this was in the mid 90s. So if you have X, so if X is a metric space, and if C is a class of metrics, so we say that X admits a stochastic embedding into C matrix if there exist non-negative number PIs that sum to 1, okay, and maps from X into YI, so where YI is actually an element in your class of metrics, okay, and you want 2 conditions, so that it's non-contracting, and 2, that on average you have distortion D, okay? And this for every pair of points. All right? So I'm gonna use the following notation. I'm gonna use that X D embeds into C. I'm gonna use this short and compact notation. Okay, so so why is this notion useful? Well, this notion is useful because if you have a stochastic embedding of metric spaces into a class of metric spaces for which you know already that they do embed by Lipschitz into L1 because of the very specific structure of L1. Like, and by this, I mean, if you take a L1 sum of L1 space, you still have an L1 space. Well, you can upgrade this stochastic embedding to a by Lipschitz embedding into L1, okay? And tree metrics are important here because it's well known that the tree embeds isometrically into an L1 space. So you want to embed X into a distribution of trees, okay? So, and how do we use it for our problem? So for our problem, you just need to prove the following lemma. So if X stochastically embeds with stochastic distortion D into tree metrics, okay, then if you look at the traveling salesman space over X, well, this also stochastically embeds into what? Well, into traveling salesman spaces over Y, where Y is a tree metric. Okay. So you want to lift your stochastic embedding at the level of the metric spaces to the level of the traveling salesman spaces over them. Okay. And the proof is completely elementary. Okay. So you just do, once you have the right definition, once you think about proving this, the proof is completely elementary. And what is crucial is that we're looking at dominating metrics here. So this condition tells you that your maps are injective. And so because of this, you're going to have a one-to-one correspondence between traveling salesman path in X and the traveling salesman path in the image of X in the Y eyes. Okay. And then you just do a little bit of computations and you realize that this is true. So this lemma, I mean, it's the analog of a very well-known lemma for the earthmover distance. So it's you can find this in a work of Sharikar, which actually builds on a previous work of Kleinberg and Tardos. And so this is true for not for the traveling salesman construction, but for the earthmover construction. Okay. Now it's actually very hard to find an explicit proof of this. It's mentioned everywhere, and it's very, very well known in computer science. But to find an explicit proof without going to the deciphering through the papers, it's not a trivial task. But anyway, the proof is actually very simple if you try to write it down for yourself. Okay, so then, well, what do you get from this lemma? So from this lemma, what you get is the following corollary: that if X stochastically de-embed into trees, then the L1 distortion of the Lamplighter metric over X is actually some constant times the stochastic distortion here. So the proof is, well, you just follow a couple of steps. So you first embed X stochastically into trees. Then you use the key lemma, which lifts these stochastic embeddings to the traveling salesman spaces. Now, if you have your trees here, these are traveling salesman spaces over trees, then you can use our previous theorem, which says that these guys here, they will embed by Lipschitz into L1 with some uniform distortion, 6. And so this will embed this space. So you can leverage this to have a bi-Lipschitz embedding of this space into L1, but then with the minor modification, you get an embedding of the Lamplighter metric over X, okay? And of course, this applies to Lamplighter graphs, Lamplighter groups, because this is these are extensions of the construction. So looking at the much more general problem, I mean, looking at the problem in a very general setting of metric spaces and realizing that you can use this very powerful reduction to tree technique from theoretical computer science, what allows you to prove this rather general result, okay? So now, why do you have this bond on the distortion that I mentioned at the beginning? Well, you have it because now there is a huge literature about stochastic embeddings into trees. And this quantity here, the stochastic distortion, has been computed for many classes of graphs for general metric spaces. And so there is a long history. So Bartal started this and got a bond of log square of the number of points, okay? And then this was subsequently improved a couple of times until Faxaron Paul, Rao, and Talwar, so early 2000, they proved that so X, any finite metric space stochastically embeds into tree, and the stochastic distortion is big O of log of the number of points. So that's why you get this distortion that I mentioned at the beginning. Now there's very interesting works on trying to estimate this parameter for classes of graphs which are topologically restricted. So I won't be able to mention everyone involved in this. I apologize for that, but there is some very interesting work of Gupta, Newman, Rabinovich, and Sinclair about outer planar graphs, graphs with small Euler number, where you can have actually a bonded distortion. There is also work from Sidiropoulos, James Lee, so Tassos Sidiropoulos and James Lee, Sidiropoulos and Indik about some classes of graphs. So I'm thinking about path width K graphs. So there is a lot of literature on this topic, and you can just use it as a black box to give upper bounds on the L1 distortion of Lamplighter metrics because of this corollary here. Okay. And well, I think my time is up, so I will not have time to talk about coarse embeddings of the planar Lamplighter group, but we can use these embeddings to get coarse embeddings and recover also another consequence of the embedding result of Nauer and Perez. But I think it's time to stop. Thank you.
That was a very nice talk, especially like a Blackboard talk. All right, so we can take questions and comments.
I was wondering, first of all, thank you very much for the interesting talk. When you define the distance between two vertices in the Lamplighter group, and you tell that this is the shortest path between the vertices, I was wondering whether this is a unique. This is unique because I kind of recall a discussion about the uniqueness of geodesics being the generalization of the line between 2 points.
No, so I mean, for a tree, yes, there is only one geodesic between 2 points, but for a general graph, you can have 2 paths that realize the shortest path, but which are distinct. Like think of the cycle. You want to go from the top to the bottom, you can go from the right side or go from the left side. So there does not have to be a uniqueness of the, no. The path.
All right, thank you. Any others?
I have a question. Is there an example of a subset of L1 such that the Lamplighter metric space over it does not embed into L1?
No.
Any example?
No.
Example.
Okay. I mean, this is, I mean, you could potentially say, well, if the space does embed into L1, why I mean, maybe the Lamplighter space also does embed. There's no counterexample to that. The only examples of Lamplighter groups or graphs that I know of that do not embed into L1 is actually because the ground graph already does not embed. But
right.
Yeah.
Okay.
Mm-hmm.
How about the Euclidean embeddings? Are they known or embedding into Hilbert space? The Euclidean embeddings. So
for Hilbert spaces, you know exactly the Euclidean distortion for let's say the cyclic or the toric Lamplighter groups. You know exactly the distortion. So the upper bounds they come from this embedding of Naur and Perez, because I just mentioned this. I forgot to mention this, but I just mentioned the embedding into L1. They were interested in embedding into LP spaces. Okay. So what the formula I wrote is just for the L1 case, but they have an LP version of that. Actually, they prove something to prove the L1 case. They go into LP, P strictly greater than 1, and then they use that capital LP isometrically embed into capital L1 to get the L1 version. But it's really an embedding into capital LP for P strictly greater than 1. And the exponent is not 1 minus epsilon, it's 1 over P minus epsilon. So, and if you go into L2, you don't even need the epsilon, so it's 1/2. And by doing this thing that I showed, you can actually compute the Euclidean distortion for the toric Lamplighter groups, and the distortion is n to the power d, which is the dimension of the torus, divided by times 1/2. So it's n to the d over 2. And the lower bound is and it's tight. The lower bound was proved by Jolis and Valette. Okay, so you know exactly. So if you want to embed the toric Lamplighter group into L2, the distortion is up to some factors, square root of log of the number of points. So this is known. It's also known for the cyclic Lamplighter groups. So the distortion is square root of log of the number of points. So yeah, in the Hilbert space or LP spaces, we know more than when we know in the L1 case.
Thank you. Any others? All right, thank you again, Florent. That was a very nice talk.
Welcome.